Hello, my name is Matt Herman, and I'm here presenting my project on cybersecurity incident prediction for CompSci 715. In this project, I'm looking at data collected through Microsoft's Copilot guided response architecture for predicting cybersecurity incidents. Now, this architecture interested me because I work in IT, and looking at cybersecurity incidents across this space is something that I deal with. But this in particular, the inference pipeline here, it runs and trains every 15 minutes. So that presents some unique challenges. Now, when Microsoft published this data set on Kaggle, they introduced or they called out metrics of accuracy and macro F1 for evaluating the data set for people who are looking to do research on it. I want to also look at the computational efficiency, thinking about how often this runs and the training cycles for it. With that in mind, I'm going to look at both neural networks and what Microsoft uses for their implementation of random forests. Jumping into the data itself, there's a few challenges that become immediately evident. First is the size. The data set consists of 1 million incidents that were collected over a 2-week period from a single region in Azure. Now, the incidents have a hierarchical structure that they are built on alerts that are built on events, and there's over 9.5 million samples in the training set, additional samples in the test set. Beyond that, the dimensionality and the sparseness are interrelated problems. There's many different attack vectors that Microsoft is trying to detect within this data set. It starts as 44 features, and you can see in this screenshot that there's a number of null values here. So that's something that those have to be filled. They can't simply be dropped in columns because based on the type of threat it's trying to detect, that's going to be valuable information. And that was true as I went and evaluated the data set later on and tried different things. When I used one-hot encoding on my small initial data sets for code development, it was sufficient, but that built out over 3,200 features when I tried it on the full data set. So I implemented feature hashing and tested that with some of the models, and I'll report on some of those differences in the metrics later on. And again, in terms of sparseness, it's a matter of filling those and then adapting it for the type within the column there. Now, the target here, we're looking at how the incident is graded. True positives and false positives are direct. Benign positives are interesting. These are cases where it's a valid event or alert, but it's not an actual threat. Think of a case where a user forgets or mistypes their password, so it's a failed authentication attempt, but it's not actually someone who shouldn't have access to the information trying to get to it. So that would be something that's a benign positive result. That's our largest case, false positives being the smallest within the sample set, and we'll also show how that reflects in the metrics later on. For the data sets, I tested 4 different scenarios here, one-hot encoding with 20 and 40,000 incidents, and then feature hashing with the same incident sizes. So this shows me the differences with dimensionality changing and also a sample size change in the results. And with 2 different model architectures, that'll give me 8 different sets to look at to be able to show trends. With that, we were able to get some interesting results, and 3 trends really show here. Starting with the primary metrics that Microsoft identified over on the right side, you can see very quickly that the random forests performed better for both accuracy and the macro F1. So it's clear why Microsoft selected those architectures to use. Now, the one neural network that was above 0.7 on both of those, that trained on the feature hash 40K data set. And that's the same data set that produced the highest results with the random forest. So that increased sample size with reduced dimensionality that had 153 features, that produced the best result. Comparatively, when using one-hot encoding on those same samples, that was 1,256 features. So that is quite the difference for using the feature hashing on that space. So that's a clear advantage of that method for the treatment of the data. The third trend is the computational time and cost. And neural networks performed better there. And that was surprising to me for a couple of reasons. First is the neural networks utilize GPU VMs, which are generally more expensive in Azure. So I assume that they may be faster, but the cost may be higher. That was not the case. We see that they're faster there. The one-hot encoded data sets with the random forests ran into memory errors on the VMs I was using. I had to move those to larger RAM VMs, and that increased the cost to actually make those the most expensive VMs in the data set here. And additionally, when we got to the larger sample size, those training times slowed down to the point that the 40,001 hot encoding, I stopped that tuning prematurely and just took the best parameter set I had at that point because it was trending to go past 35 hours. And I wanted to ensure I was able to complete the training of the model and reporting the full metric set for the project. Based on these findings here, let me go back a slide. But based on the findings there, I think the next step would be to try and use an architecture like a neural forest. If we can use the computational efficiency of a neural network, but use small models that limit the scope of the features and the depth, and take advantage of some of the benefits of an ensemble with them to achieve higher metrics, that may be an approach that kind of takes the best of both worlds while continuing to use feature hashing or similar methods to reduce dimensionality within the data set. Now, some additional metrics here, looking specifically at the ROC curves and AUC scores. Throughout the metric sets, the random forest model, these were the best performing from each architecture here, but the random forest model outperformed every step of the way, but they were consistent in how they performed on each of the classes, with the false positive performing the worst as the smallest sample size or the least represented class. If I were to rebuild my data sets, I'd probably, for convenient math, change it to a total of 45,000 incidents and select 15,000 of each class and see if evening out the size would boost the false positive result and then the overall averages for it. With that, let's shift over to look at some of the code and the notebook here. For the testing and running of this, I ran a lot of parallel things, and I've copied the results in the output here, and I'll just highlight a few things for this presentation, starting with the neural network and the methodology here. I use the same methodology on the random forest with obviously the different library for that and then parameters. Both of them, once the data is prepared properly, come in and I use an optuna library function to be able to set ranges for parameters and then run trials to find the best set of parameters for that. I also implement a hyperband pruner so that I can do a partial fit and then prune any trials that appear to not produce a result that will be competitive with the results already produced. And I selected this example from my early development because it was highly efficient in pruning and limiting that tuning time. Once I have a best result, the code continues to use some functions to train and save a model based on that best result. I extended the patience parameter here to see if it goes further into the epochs. And then I'll go ahead and create predictions off of that so that I have metrics to report and compare from. Further in the notebook, as I scaled up the data set, I tried a number of different things, and I documented some of those attempts here in this unsuccessful experiments. It's good code and valid techniques that I likely will use on other data sets in the future, so I wanted to go ahead and preserve that there. In the data preparation, I won't go into the specific code, but I do call out the differences for using the feature hashing versus one-hot encoding. And I specifically would prepare the sets and save them out to Google Drive and Parquets, and then re-import them to ensure that I was training both architectures on the same data set and that I didn't have variance there for what I was using. The last main section here is where I have the metrics detailed. And then for the top performing models, I have the additional metrics and the detailed runs for each of those. And then for every model I reported on, including at the bottom here, I have my one error for where I had the early stop on that parameter tuning and then built out the model and completed the metric collection. Thank you for watching my presentation today. I hope you enjoyed it. I certainly enjoyed exploring this data set, and I look forward to doing some additional research and seeing different ways to improve both the efficiency and the metrics on it. Thank you.